The Sanctuary of the Great Gods on Samothrace is a physically remarkable place on Earth, whose assets were recognized, manipulated, and aggrandized in the service of a potent soterial cult. The remarkable expansion of the sanctuary from a regional to international center in the late 4th to 2nd centuries BCE was coincident with the transformation of Greece into a Hellenistic world, and it bears witness to the urgency and perceived efficacy of the cultic promises in this expanded environment. Research in the sanctuary reaches back to the 15th century, and excavations by French, Austrian, French, Czech, and American teams have unearthed an extraordinary array of novel buildings and, of course, statues. In building upon the past research, our team have reframed the archaeological investigation of the sanctuary to emphasize the powerful environmental factors underlying its rich material record and the human actions through which people determined and experienced it. We also have explored the significance of connective passages and spaces that join key regions of the sanctuary, and we have investigated the sanctuary's central feature, the channelized water torrent, as a major monument in its own right. We thus affirm what has long been recognized, the significance of the Sanctuary of the Great Gods at Samothrace as a locus where local and international ambition and patronage meet with innovative results. But we also approach the sanctuary from the ground up. It is an evocative place where landscape and human interaction were integrally interwoven, and where the local terrain, local materials, and local community have at least, if not more, of an impact on the creation of the sanctuary as it do its famous Hellenistic patrons. In this colloquium, we would like to share with you some of our initiatives that have been shaped by privileging research questions that center on the interaction of terrain, materials, architecture, passages, and human experiences of moving and seeing this sacred environment, moving through and seeing this sacred environment. Although there are only 4 of us here today, we are indebted to our whole team on whose hard work we have relied, and we share the results on their behalf. Now, the innovative marble buildings, many gifted by Hellenistic royal and elite patrons, are the hallmark of the sanctuary. And here you see the Huron, crafted of Thasian marble, as are many buildings in the sanctuary. In 2007, we began working with Yannis Maniatis to identify the marble types used in the sanctuary, and this work continues as we build our understanding of the exogenous materials that define the built environment. But every one of these buildings rests on a foundation of local stone, and its formation and use plays a vital role in the history of the sanctuary. Since 2013, Professor Bill Size has joined our team to create a classification and source the local rock types which were used in the construction of retaining walls, service buildings, foundations, and channels that shape the temenos and rise organically from its soil. He will speak first on this research into the formation of some of the sedimentary rock types used in the sanctuary and their quarry sources. I've spoken of the fame of Samothracian architecture, which is well preserved even though no longer standing. Since the 19th century, the focus has been on architectural reconstruction. Highly influenced by modern aesthetics, the mode of presentation was the elegant but disembodied inked drawing. We have aimed to return the buildings to their landscape and materiality through 3D modeling. Digital specialist Ian Burr is responsible for those renderings and animations, and he is with us today to answer any questions you might have regarding this work of 3D modeling. Because this seminar program addresses historical geography and geoarchaeology, we wanted to share with you our work on the most dynamic and defining feature of the sanctuary, the natural torrent, which runs right through the heart of the temenos. Getting from one side to the other of this channel was also as much of a challenge in antiquity as it is today, and we've employed various strategies to determine where and how it might have been bridged. That work centrally involves the theater. And I'm going to try to pace ourselves so we have time to share with you this recent work led by Andrew Farrenhold and its impact on our understanding of the complex architectural topography of the southwestern sector of the sanctuary. And one of our objectives has been to repopulate the sanctuary. The cultic rites of initiation, the mysteria, were kept secret. We cannot know them, but we can tease out the ambient experience generated by the landscape, by moving through it, and by the position of monuments. Here again, 3D modeling is invaluable, and we will share our fixed platform animations with you. But we also like to introduce to you some work done by Arya Basu, computer specialist and in the Emory Center for Digital Scholarship, on the work of agent-based modeling as a way to understand crowd dynamics within the sanctuary. So those are the areas we plan to share with you today, and I'd like to turn the seminar now over to Bill Size.
All right, so thank you very much for the invitation, along with Bana. A number of years ago, Bana asked me to look at some of the rocks from Samothrace that she had brought back, and then they were so intriguing that she invited me to come over to the island to take a look at some of the rocks and see what kind of plan we could come up with to show the importance of the rock, the local rock, used in the sanctuary. And that turned into the past 5 or 6 years of collecting rocks, both within the sanctuary and outside the sanctuary, doing comparisons, trying to do provenance study, and what a geologist like myself would call petrogenesis. That is, where did the rock come from and how did it form? So what I'd like to talk with you today a bit is about the local geology surrounding the sanctuary of the great gods and the type of stone material that they used in the sanctuary, where the quarries were located. Some of the quarries, we haven't found all the ones we would like to, and then why they would use that particular type of stone, not that it was just a local stone. So on this first slide, you see some of the interesting things about the island of Samothrace. You see it has vegetation. You can see the green growing up the slopes of the mountain. That's unusual for a lot of Greek islands. It does get a good deal of rain and snow. And so there are streams coming down out of the mountains. They're mainly intermittent streams, but when they do flow, sometimes they're catastrophic. They're torrents. And Bana mentioned they go right through the sanctuary. And it begs the question, why would they put a sanctuary in such a dangerous geological place? But that's a bit of a question still to be answered. What you also notice is it's a very high-peaked island. It's almost a mile high, 1,600 meters high, and it's a small island. So the gradient from the top to the sea is very high. And so meltwater and rainwater coming down can reach a very high speed, and it can move quite large boulders during flood stages. The red circle shows where the sanctuary is located, and other shots will show that it's at a confluence of at least three streams, and so you have the increased damage that can be done during flood stage. A bit of the geological setting. Here you see Samothrace Island in the northern Aegean Sea, and just offshore you see this darker blue water. This indicates deep water, obviously, and it is a trench. It is a crack in the seafloor, and it is moving. It is a fault that is quite active. You know, a number of earthquakes are generated along this zone fairly recently, and that explains part of the history of Samothrace, its dynamic or tectonic history in the area, and also accounting for the great variety of different types of rocks. Because when the fault moves, It brings up rocks from the seafloor above sea level. They become part of the terrestrial environment then and subjected to erosion as a result of that. So another slide on the geology from a larger scale here in the red circle is Samothrace. In yellow, you see active faults. The one that skirts the southern side of the island of Samothrace is called the North Anatolian Fault. It is quite active with earthquakes and movement along the plates. If you can see the black arrows on either side of the yellow line, this is the direction of movement along the fault. Different types of magnitude of earthquakes usually indicate the relative amount of motion, but this is a very active fault. And it's the result of two very large plates, the Arabian plate, this is in plate tectonic theory. The Arabian plate in a large yellow arrow indicates the direction of movement of the Arabian plate at about 3 centimeters per year to the north. And the Anatolian plate, a smaller plate, moving in a counterclockwise motion at about the same rate, but one is pushing against another one. And down here we have the African plate, and where some of you are sitting right now in Paris, you're sitting on the Eurasian plate. They're all moving, some faster than others. And fortunately or unfortunately for Samothrace, geologically it's fortunate, the fault is quite active. And the plates are moving because of motion underneath in the mantle, but that's another story. So just a simplified geologic map of the island, showing you some of the variety. First, you can see the dimensions of the islands. It's quite a small island, and it has a lot of variety. The oldest rocks are a few metamorphic rocks of Mesozoic age occurring through here. They are not used as construction stone in the sanctuary, as far as we can tell. The next oldest rock is the basalt, shown in green, greenish blue, that you see here. These are what we call late Jurassic, about 154 million years old, which geologically is young. And these are from the seafloor. These rocks in basalt that you see through here have been thrust up along that great Anatolian fault, and they represent former seafloor rocks, and we have very good evidence for that. This basalt rock is volcanic, obviously, and it is exposed in the sanctuary by the letter S here, where the sanctuary, it is exposed in the sanctuary and produces some of the ridges that are within the sanctuary. Another rock is in pink here, which is granite. It's quite young. It's only 14 million years old, and it was thrust up again along the fault. The Great Anatolian Fault comes along here. And as some of you know, if you've ever gone along this shore, it's a very sharp cliff face through here. And just offshore is a very deep trench in the seafloor representing the Anatolian Fault. And this is where the movement occurs. So we have rocks that were once deep-seated within the crust of the earth. We have rocks that are former seafloor rocks. And then we have the rocks that are produced from the erosion and weathering of these two types of rocks and others. And so these rocks that we collectively call alluvium are being washed down by the force of gravity and rainwater, and they move down through the valleys. They see in these little arrows going through here. And the alluvium is being shed out into a plain, and the sanctuary is partly built on one of these alluvial plains. And it's composed of the of the material shed off from the highlands of granite, basalt, metamorphic rocks, and other types of rock like that. So that sets the stage for the types of material that in the natural process formed the rock that was used for the building stone foundations and walls in the sanctuary. This alluvium is quite actively moving in geologic terms, and is moving obviously towards the shoreline and then offshore due to the action of the waves. And so what we have for the rock types on Samothrace used in the construction is a combination of two different environments. This terrestrial environment that's above sea level being weathered and eroded away and under the forces of gravity and water and atmospheric air and biologic activity. And so we have this terrestrial environment that moves material down to the shoreline where the two environments of the marine environment meet the terrestrial environment. And this is where the story actually begins for many of the rocks used in the sanctuary. So just a quick sketch map of the sanctuary that we're talking about. Just a few of the places here. There's too much to talk about today. And Bana mentioned the three streams, one here, a central one, and one just off the map over here. They're dashed blue lines, if you can see that, because they're intermittent. Many times they're just dry streams, but other times in flood stage, they are terrific in the amount of material that they can wash down closer to the shoreline. And this is how the material makes its way under the force of gravity and then under the force of moving water down through it. Another thing to mention is that here's a scale down here. The sanctuary is quite small. This is 50 meters. So the width of the sanctuary is like 2 football fields. But it'd be very hard to play football on these fields because we have a stream over here, so it's low here, it comes up to a higher plateau, it goes down to this stream, it goes up to another plateau, it goes down to this stream, and then up to a very high mountain ridge on the other side. So it's very uneven topography from place to place. And so you really have to travel up and down if you want to get through the sanctuary to it. And you can also see by the closeness of the contour lines that it's very steep in here. Again, why did they purposely put the sanctuary buildings in this site? It's a question that is a bit controversial, but it might be that they wanted to be closer to the forces of nature. Okay, so this is some of the work that we've been trying to do over the past five or 6 years, is to go to each of the sites and try to identify as many of the different rock types as possible. Not qualitatively, but quantitatively. And that was the work that we've been doing. The Theatral Circle is just an example of it, showing in the different colors the different types of rock that were used as construction stone for the flooring, the walls, the seating area, and things like that. So one of our jobs over the past years is to encapsulate the variety of rocks, sedimentary rocks, igneous rocks, metamorphic rocks, minerals that were used, come up with a classification for these different types of rocks that hadn't been done before, come up with a color code for the different types of rocks, and then showing where these different rocks occurred in the different buildings throughout the sanctuary. So in this case, we have quite a variety. In the Theatral Circle, we have quite a variety of different types of rocks. Again, it's a bit conjectural about why did they use such a great variety of rocks? Was it just that it was the only thing available at that time, or they really wanted to show different colors and textures for the rocks? Compared to the Stoa, which is not in the right position, geographic position in the sanctuary, the Stoa, 100 meters long, is almost monolithic. This brown, pebbly Dolomitic limestone. It's a little bit off the screen. This is a Dolomitic limestone in the brownish color that you see here, and as a foundation stone to it. And so very simple type of lithology used in the Stoa compared to the H-circle. So this took quite a long time to come up with. First of all, the mapping and identification of every single stone used in these different buildings. So, getting on to how did these rocks form? I mentioned the alluvial fan before. Here we see ridges. Here's the sanctuary, first of all. Here we see ridges of hard rock. This is basalt. Further upland, we get into the granite zones. And then shedding off, we see these river valleys and avalanche valleys that move the material, the weathered material out of the highlands, and slowly during different storms and different floods, move the material down and out and flushing out into the lower elevations as a large alluvial fan. And see, you can just see this structure through here. This is a large alluvial fan. If you dug into it, it would be sand and gravel, pebbles of granite and basalt, different pieces of different sizes. And this is moving. The alluvial fan is moving, usually during major storms and flooding stages. Well, eventually, this material makes it down to the shoreline. That's not the end of the story. That's just where the terrestrial environment meets the marine environment. And so the beach material is that interface between the two different environments. And so we want to look at this material because this becomes the formation for the rock material. So down here by the beach, the sanctuary is just upslope from here. We see this pebble beach. And when you look at the material in the beach gravels and pebbles that you see through here, we have this huge variety of different rock type materials and different mineral types that have come from the rocks themselves. So if you pick up a handful of this stuff, you would see all this variety in different proportions depending on where you are on the island. But here you can see mostly it's this medium green kind of color, the basalt, and the lighter material, quartz grains and things like that. So this material itself will not form rock. You have to have some way to cement this material together to what we call lithify material. So here in the beach, it's not going to happen. So what has to happen is from the wave action, this material is moved offshore, is moved offshore and is buried by younger and younger material washing off. And in that buried sediment offshore, we get the carbonate types of deposits that are forming from the marine organisms that live out here, like coral. And so in this environment, the calcium carbonate that the coral and other fossils are made of start to interact with the grains of material offshore and start to lock them together and compact them into a rock. So what happens is that here you see, this is at one of the quarry sites along the shore. What you see here are the basalt pebbles of different size, quartz pebbles, granite pebbles. This is the material that formed offshore, not here onshore. This formed offshore and has been uplifted due to tectonics, that we now see this part marine, part terrestrial rock exposed along the shoreline. And the brown material is the calcium carbonate, the cement that formed offshore in between the grains, locking the grains together. So we call it compaction, cementation, and then lithification into a rock. And this is a very common material used in the sanctuary. And you see that here on the shoreline that we see holes. If you can see them at this magnification, you can see holes. This is where the pebbles have been plucked out by wave action and by dissolution of calcium carbonate, which loosens the area around the pebble, and it falls off. And it forms new beach material that you see here. And so this type of rock is part marine and part terrestrial. And it's a pebbly limestone, the lime coming from the calcium carbonate and the pebbles coming from the terrestrial. The next shot is just a little bit back from this one. Here's the shoreline over here, and you can see the bedding of these rocks, slightly tilted, but this is a marine rock and a terrestrial rock. It formed underwater, shallow water. It formed underwater by cementing the material together, and then as time goes on, it formed a younger layer on top of a younger layer on top of a younger. And so this is bedding or stratification that is going on. These are quarry blocks that you see here, partially faced off into a rectangular blocks. And you can see that it has these big holes in them, which we call vugs, V-U-G-S, vugs is a funny word, and partly with the pebbles still in them. So it was a fairly easy rock to sculpt and to carve into blocks. So this is the type of material that they use for the foundation material in the sanctuary. And it doesn't look like it's very strong, but it's unbelievably tough rock. And in some of the buildings, and I'll go into the sanctuary, and I'll show you this rotunda, Arsinoe, through here, and as one of the examples of where they use this type of rock. So Bono showed you this shot early on. This is the wall of the rotunda, and it's in some places 12 or 13 courses high. And you can see it's the same rock that was along the seashore. It has these big vugs in it, and when you get closer up, you can see that there's still pebbles inside of here. Here is a map view of it, and the yellow indicates this what we call vuggy pebbly limestone. The vugs being the holes, the pebbles that are still in there, and the matrix being calcium carbonate or limestone. So it makes a very strong structural material for the walls. I carry a hammer with me outside of the sanctuary, and when you hit this type of rock with your hammer, it just bounces back. It's an exceedingly strong rock. So this is one of the common building stones used in the sanctuary, and I hope you have a feeling now for how it formed by the combination of terrestrial material making its way down to the sea and then offshore being buried and cemented by the calcium carbonate from marine organisms such as coral. A close-up of it shows you this buggy, pebbly limestone. Here you see the vugs, the holes. These holes used to be where they were once pebbles. And as the cement weathered and dissolved away, it opened up and the pebble fell out. And we can see this all over the place, where sometimes the pebbles are still inside, and you can almost pick them out with your finger for it. The block down below shows, yes, some of the bugs here, but mostly we have the pebbles still in there. And again, the pebbles are of a great variety. You see a lot of basalt through here in the stone. So this was used in many of the buildings as their both foundation and wall material to it. Okay, let's show you a different example. The Nikkei site on Samothrace. It's a small site carved into the side of a fairly steep slope material, and when you take a look at it, it just kind of cut into the hillside type material here. Here is the rotunda that we just showed a second ago to it. So when you take a look at this rock, again, here is the stone type, what we call a stone type map, showing the different color coordination for the different types of rock. Here was the victory at Samothrace statue, the Nikkei, slightly angled off in one direction. One thing you do see from the scale down here, this is 5 meters. This is a very small little incised into the wall of the slope. A very small space. And it consists mainly of 2 main types of rock. Here in the kind of a purple, we see what we're calling a calcareous. Calcareous means calcium carbonate, sandstone. Sandstone means that the grains are made up of a certain size particle, maybe from 0.2 centimeters up to 1 centimeter, or 1 or 5 millimeters for sandstone. That makes up the wall and the foundation for the Nikkei site. And then in green, you see basalt. These are fairly large boulders that you see here. And one of the things that some people have noticed is it seems like these basalt boulders are arranged in some type of an order. Whether this is by chance, that is, it's landslide material and just came to rest down here, or this was purposeful, that they put these basalt blocks here for a real purpose. And what that purpose was is a bit controversial. And so now the restored Nikkei in the Louvre, showing the different types of marble located in this space, slightly tilted. Whether it was a covered building or an open roof building, or that's something for Bana to tell us about. All right, let's take a look at the rock. So here's that big boulder that was in the last picture, and Bana and her students are measuring some of the foundation stone used in the Nikkei site. So we'll look at both the foundation stone and basalt boulders through it. So she's measuring a block over here, but we're going to take a look at this little piece over here. Here's a close-up of it. First sight, it looks like this construction stone was sculpted. You see these parallel lines that go across like this. But on closer inspection, you can see that this is actually sedimentary bedding. This is a geologic formed material from, these are different layers of sand and silt and pebbles that were deposited during different events. And sometimes it was high energy events, so you have big pebbles. Sometimes it was a low energy storm offshore, and it produced mainly sand. And now it looks in this fashion because they weather away differently. They weather and dissolve away at a different rate. And they form this in and out type of, almost looks like it's sculpture, but this is natural sculpting that we call differential erosion to it. So this is the type of rock you can also probably sense that it's friable, that if you put your hand on it, the grains would brush away. And that's true because the cement that's holding the grains together is dissolving away in the terrestrial environment from the rainwater. It's slightly acidic. And calcium carbonate, which is the cement used here, and acidic rainwater don't get along very well, and the calcite cement will dissolve. So let's take a look at a little bit closer look along the shoreline. We haven't actually found the quarry for this stone, but along the shoreline, above some of the pebbly limestone, we do see these big sandstone beds. The big sandstone beds, and when you look at them, they look very similar to the building stone at the Nikkei site. It's mostly sand-sized grains with a calcium carbonate type of cement, but we haven't found this as a quarry. Okay. So going back into the site and looking at a close-up of the Nikkei stone, we see all these pebbles. This is jasper, very durable material. That's a quartz grain. We have basalt grains. These are millimeter-sized grains, and the whitish material is calcium carbonate cement. So we have named this rock a pebbly calcareous sandstone. Calcareous means the calcium carbonate cement, sandstone meaning the sand-sized grains. Other people might call this a sandy limestone. I prefer not to call it that because the lime is mainly the cement, and I would rather name the rock on the basis of the grains that are in the rock rather than the type of cement. So a calcareous sandstone is the preferred name right now. A little closer look at it in what we call a thin section of the rock. It's composed of shell fragments and grains or class of calcium carbonate, basalt class, mineral class of jasper, mineral magnetite, quartz, with carbonate cement, this kind of a tan brownish stuff, and then pore space, these empty spaces that you see here that are typical of sedimentary sandstones, that you have a lot of open space to it. And so you can see that there are fossil fragments in here of gastropods and pelecypods and coral and things like that, cutting through here. So so this type of material was the typical building stone in the Nikkei site. And if you can see, let's see if I can move this thing out of my way. The chemical analysis shows that silica, meaning quartz mainly, very high percentage of it's mainly calcium oxide, 45% by weight, and LOI, which means loss on ignition. That is, when we analyze the chemistry of rocks, we heat them up to 400 or 500 degrees centigrade to get rid of the water, and it also gets rid of carbon dioxide, which CO2 combined with CaO makes calcium carbonate. So when you see these two numbers of calcium oxide plus a lot of loss on ignition, it usually means the CO2 gas, which means that the calcite is decomposing into calcium oxide and carbon dioxide, which goes off as a gas when you heat it up. So it indicates there's a good deal of calcium carbonate in here, but also a good deal of quartz grains through there too. Okay, so let's take a look at the basalt now that may or may not be in the structural formations that are here. Basalt was used a lot, say by the Romans. Back here is a Roman wall, but it's very hard. It's hard to carve it into blocks. And so they use freeform usually. When they do use basalt, it's usually a freeform type of material. And it's a very common rock on the island. When you see a clean surface, this previous surface is full of lichen and other types of stuff. When you see a clean surface, the basalt, it has a very unusual feature. It has these pillow, they call them pillow-like structures. They're blobs of magma that have crystallized. They're blobs of magma. We call it pillow basalt. It's a funny word because they're kind of rounded. They have gas bubbles in them. They're kind of rounded. And in between these chunks, we have mud, marine mud that has turned into jasper. And so the jasper fills in the spaces between it. We call this a pillow basalt. Call it a pillow basalt. This only forms on the seafloor. And here in the sanctuary, this rock has been uplifted due to tectonics into these ridges of basalt, and it's used in the sanctuary as decorative stone sometimes. In other places, it looks like it was an altar stone. That this stone may have been revered. It is revered by geologists because it's very primitive just to the formation of the earth. But archaeologically, it may be a stone that was used for sacred processes in the sanctuary. It's a beautiful rock, but very hard to fashion into blocks. And then a quick shot at a thin section. This is only 5 millimeters across. And what we see here in the basalt are these different minerals: plagioclase, feldspar, pyroxene, magnetite, and then the ground mass, which is this darkish material, which is so fine-grained that we can't identify what it is. But these are feldspar crystals and the pyroxene crystals, a typical type of volcanic basalt. The chemical analysis shows that very high amount of silica, but also high amounts of iron, magnesium, calcium, sodium. These are the typical elements that go to form an igneous rock crystallizing from a lava. But it produces a very hard type of material. But it's used throughout the sanctuary in free form. All right, let's visit the Stoa site. I showed you a picture of this before. You're seeing the foundation, a little bit of the walls, and then the storage yard for the blocks around it. Very long, about 100 meters. It had to be filled in at this site to build it up to make a flat surface, a fairly flat surface on it. So here are some of the blocks from the Stoa. It's a Dolomitic Limestone. Dolomite means that it has magnesium, the element magnesium in it. And dolomite forms the magnesium forms a mineral called dolomite, which is magnesium calcium carbonate. And the rock itself would be called limestone. So in some cases, it can be carved quite easily. It's a soft material. When it's carved like this, you see the bugs or openings in it. These bugs are due to a different process than the one we talked about before with the pebbles plucking out. When it occurs in a slightly more dense form, it can actually be sculpted that you see through here. But still, you can see it's kind of rough, kind of a rough surface to it. That's because marine rocks, when they get above sea level, are interacting with terrestrial environments, and we get selective dissolution. All right, well, let's take a look at where these blocks may have come from. Down along the shoreline, we found what's left of a quarry. Most of the quarry is underwater. When When we take aerial shots, we can see that the quarry continues offshore. We see partially quarried blocks through here. And the size of these blocks and the size of the blocks in the Stoa are practically the same. Chemical analysis of the two rocks in the Stoa and along the shoreline are almost exact to it. Easily quarried stone, but once you get out of the marine environment, it is subjected to the weathering environment of terrestrial rainwater and biologic activity and wind and things like that. So this seems to be the source. It's a reef, a marine reef type structure. It's composed mainly of marine coral reef material and fairly easy, as I said before, to make. But one of the interesting features is when you look at a close-up, a centimeter scale, of here at the quarry along the shore, and then in the Stoa, in the sanctuary, you see the coral structures here. And along the shore, it's kind of a brownish color with the coral sticking out from the cement around it. And when you go to the Stoa, you see that the coral is in negative relief with the calcium carbonate cement as a positive. So we have a reversal of relief structures from the marine environment to the terrestrial environment. So it shows you what can happen to a stone as you move it from one environment to another. It can be quite drastically changed around. So a close-up, again, a thin section of the Dolomitic Limestone shows you fossil fragments of coral, some gastropods and pelecypods and things like that. It has a little bit of quartz in it, the SiO2, but it's mostly a calcium magnesium carbonate, CaMgCO3. So you can see these very large numbers for the weight, and then a very large number for the carbon dioxide to make the magnesium calcium carbonate. This is a nice looking fossiliferous limestone, but it does have the magnesium. I emphasize the magnesium because the dolomite is actually a secondary process from seawater, and I'll explain that in a second. Other blocks in the Stoa have these large bugs in them, very large bugs, which are dissolving and getting bigger and disintegrating the rock, basically. Again, these bugs or openings are not due to pebbles coming out of it. They're due to the dissolution of the fossils and then enlarging that area around where there used to be the fossils. So many of the Stoa blocks are disintegrating. When you take a look at it in thin section, this is what's happening. The Dolomitic limestone shown down here at the bottom is being converted into dolomite that you see here that completely destroys the structure of the rock, and it opens up big bugs as it's doing this. So this magnesium has come in and dissolved away the calcium carbonate and has replaced it with calcium magnesium carbonate, and in the process is basically destroying the stone. And as far as the building stone, it falls apart. In conclusion, I'd like to just point out that there are two ways that the main building stones in the sanctuary were formed. The first one is the progressive dissolution of carbonate matrix cement and the plucking out of pebbles here that we see here. And these voids then serve as the focus for enlargement and coalition of bugs into large cavities. So this used to be the stone that had a lot of pebbles in it. And when you put it into a different environment, it starts to dissolve away the cement and opening it up, and the pebbles fall out. And these bugs get bigger and bigger and bigger as time goes on. The other process is the one we just showed you, where we have the progressive, what we call dolomatization. That is the conversion of limestone into dolomite by introducing more magnesium. And so that produces a volume change. It causes the material to dissolve away, which are centered around the fossils, and that opens up the bugs into larger and larger bugs that start to coalesce. So the bugs you see here used to be where the coral was and other fossils. They're selectively being dissolved away from the rock, opening up huge spaces. And unfortunately for this rock in the Stoa, the bugs get so large that the rock disintegrates. And that is what we see going on in the Stoa right now. So a last picture, Bana showed you this of an oncoming storm. I think Bana may show you some photos of the destruction that can happen in the sanctuary due to the torrents that race through the sanctuary during heavy periods of rainfall. And geologically, obviously, it's a very important process that modifies and changes the landscape, carrying, first of all, moving the material downslope towards the shoreline, and destroying the landscape and modifying it into a different type of shape. So earthquakes, landslides, stream erosion, all under mainly the force of gravity and plate tectonics, are what have modified the sanctuary. And it's progressive. It's still going on. And Bana may show you that the website that you can go to see some of the simulations that have been made, will walk through the sanctuary. So I think I'll end there and maybe wait for Bana and the others to finish up if you have any questions. So thank you for your interest.
Thanks so much, Bill. You can see how vital the petrographic work is to our understanding of the sanctuary, and also to our the future of the sanctuary, because one of the issues that we confront, and that those of you who've come to Samothrace know, is the disintegration of the exposed stones, particularly at the Stoa, which has some 2,000 blocks that survive. And yet, as we, at the request of the Greek government, have been asked to create an anastylosis, we, of just even one column, we worry that the stone has the strength to stand at this stage. So, but we're working on it, and with Bill's expert guidance and those of structural engineers, we hope that we might be able to make this Stoa look a little bit more like it was originally. Now, I would just, I'd like to share with you all a few of our initiatives that emanate from Bill's work, and then also some others. But one thing that Bill mentioned, which I'd like to point out, is how much his work has impacted our understanding of the building history of the sanctuary, because these limestones can often, we can tell them visually apart, but not always. And generally, there were names that were very evocative to the original excavators, but did not have scientific meaning, like salt and pepper and crumbly yellow and marine. We all knew what the excavators meant by those names, but they didn't have geologic resonance outside of our very small group. So giving names to stone has been crucial, but then also differentiating some of the types of limestones that has been crucial. And what we realized, once we had mapped every foundation stone in the sanctuary, and you're looking at that plan now, we began to see patterns that we found were really informative to us. For example, our earliest monuments, and I think you can see here on the far left, the Hall of Choral Dancers and the actual circle were made of many different materials, and actually some of them were reused. So in this early stage of monumentalization, we have both a kind of an archaeology preserving earlier structures whose foundations we have not yet found, but also the kind of opportunistic use of a variety of materials. Then when we move into the third century, the late fourth and early third century, the period of tremendous building activity in this sanctuary, we have a real consistency in the use of that vuggy limestone that Bill talked about in the Huron, the Rotunda, the Propylon, the Neorian, and these buildings have been, at least two of them are associated with Hellenistic royalty by signature, the Rotunda and the Propylon. But we also wonder if the Huron might not also be a royal dedication. And any of these all cluster into this very intense building period. And coeval with them, but distinctively different, is the material of the Stoa. We wonder if that isn't coming from a different source of patronage. The superstructure of the Stoa is also made of limestone, which suggests maybe it was a locally inspired building, whereas the other group that we're looking at with the vuggy limestone foundations seem to be by royal patrons or highly elite ones. Then we have a few buildings that are made of other materials local to the island. And of course, the one that interests us and that Bill has already talked about is the Nikkei Monument. You'll notice that its stone, that calcareous sandstone Bill spoke of, doesn't really show up elsewhere in the sanctuary. And that was a very important piece of evidence for us. Let's just turn to the Nikkei Monument for a moment. We won't dwell here. It tends to be the monument everyone is interested in, but it's not our full story today. And of course, you are right around the corner, some of you from the Louvre and the statue itself. But in Samothrace, it took pride of place at the top of the theater, and we're looking into the sanctuary in this view from where it originally stood. Now, I mentioned earlier that most Samothracian buildings, even though they're not standing, are very well preserved. But the Nikkei Monument is not. It really is stripped down to, whoops, go back. It's foundation courses, and only at the back of the monument, which you can see on the aerial view on the right, is it preserved to the second step. The other interesting factor is that most Samothracian buildings are made of really nice materials, that is in their superstructures, marble typically, but the Nikkei Monument is not. It's made of this calcareous sandstone throughout, and it rests on a packing of boulders. Bill has informed us that it is the only building that is made of this material, and that helps us actually understand some of its building history. Because while it is itself the only ancient building made of this material, we do have another building in the sanctuary which is largely made of the same kind of calcareous sandstone. It's down the hill from the Nikkei Monument, and it's a Byzantine factory. And I'll just show you in aerial view that shows you where the two buildings are. You can see on the lower right-hand corner some of our team members actually marking with small green tags all of the stones in this building, which are of the calcareous sandstone and seem to have been cut up from the Nikkei Monument and transported about 120 meters to the north downhill to form this factory. So that actually helps to explain in part the current situation the Nikkei Monument. Now, it doesn't explain whether or not the building was, as Bill pointed out, one of our chief issues. It's trying to come to terms with whether or not the building was originally roofed or it was an open precinct. Because of the 535 pieces we found in the Byzantine factory, none of them have an architectonic feature. They don't have a flute or a molding or form part of an epistyle that might allow us to understand the design of this monument. We do have some small fragments that are molded that have been turning up steadily in the courses of excavation, some quite recently in 2019. All of them hint towards an Ionic style building, but it's really worth bearing in mind that if you look at the size of the blocks, even those that are complete and remain in the Nikkei foundations, they're very small. And so it would be very difficult, in fact, to span a colonnade in this material, impossible. So we're still very much trying to make a determination on whether that building was open or roofed, and the quality of the stone and its capacities play a role in that story. I'd like at this stage actually to shift to another aspect of our research that I think this seminar might find interesting, and that is the impact of water in the sanctuary and also its role in the sanctuary. And Bill mentioned a couple of times from a geologic perspective, he didn't think it was such a great idea to be building in this area. But I think that the reason why is because it was the very geologic energy that was resonated, and the power of this water torrent that ran through the Central Valley was also important. All of the earliest deposits that we find are actually right along the stream bed. Right, just on the eastern side, that would be the upper part of your screen. But so it's really clear that this particular feature was actually the important one in this valley and gave it some of its defining sacredness. But it also created a great deal of volatility. And that's one of the things that we've been exploring. It's the way in which they both honored this natural feature, but also attempted to control it. We could go, just so we could look, I think you got this very clearly from Bill's presentation, but just to show you again the topography and geology of the region with the three streams that both bisect the center of the sanctuary and frame it to the east and west. Here you can see on your right. And you can see on the lower left the way in which these torrents have carved through the alluvial plain that Bill mentioned to create basically the defining boundaries and plateaus that form the sanctuary. And one can just see in that lower right-hand image the top of the Huron columns rising up into visibility. So you can see how deep that Central Valley is. We can take a look here. This is the aerial view again, just to give you a sense of also how sharply the channel diverts from its course and hugs the western side of the valley. And we wanted to understand whether that was a natural phenomenon or an anthropogenic one. To what extent has this channel been forced into its current course, or are the builders simply just channeling and controlling right on the stream bed? So we've taken a number of approaches, but I want to also just reiterate what Bill said about the power of this feature. It can often be dry, but then it can become extraordinarily active in just minutes time if there's a huge storm. And I want to just share with you, this is not by any means the worst storm that happened in the year 2017, but it gives you an impression. That was just in the space of about an hour of torrential rains coming off of that mountain. So here, and that force needed to be controlled, and we see that happening with two different kinds of retaining walls that we roughly label Greek and Roman. Probably Hellenistic wall made out of those great basalt boulders that are piled up to channelize the water. And then on your right, you see the Roman version of these that are made more of concrete and smaller blocks and rubble, built up sometimes on top of the foundations of the boulder wall, sometimes in front of it. The course shifts as the dynamics of the stream and its destructive forces require. Now, understanding the relationship of the channel and understanding how people got from one side to the other in antiquity has been a matter of interest since the American team started working in the sanctuary. And I show you a series of plans. I won't dwell on them because our time is short, but in this first plan of 1955, I think you can see that the channel is actually not within any boundaries. It's actually operating this broad area here. Eventually they do canalize it, and let me see if it's there. And you could see that they only imagine one crossing in the area of the theater. In the plan of the 80s, they imagined two crossings in the area of the theater and then also west of the Rotunda. And in the plan of 1998, there was a major change that was made in this our understanding of the Central Valley. You can see that the major building right in the center, which we now call the Hall of Choral Dancers, has replaced an earlier structure, which was known as the temenos, and it is basically twice as wide and has a porch facing to the front. That actually touches right against the edge of the channel. And it became clear that, that our passage that we had reconstructed was impossible. If you come down the Sacred Way from the Eastern Hill, as you see here from number 24 down past the Hall of Choral Dancers, we can cross over to the western side, but then you can't actually access anything because of the reconstructed design of the theater. And if you try to come along anywhere on the eastern side of the channel, that was impossible too. You were blocked at the front. So there was literally no way to actually get to the southern heart of the sanctuary with the Huron, altar court, and Hall of Votive Gifts. So we realized this was a problem, and the way in which my predecessor, Jim McCready, who was always a man that believed in Occam's razor, you take the simplest solution. He said, well, maybe it was just covered its entire length. And so that was the plan that was published in 2002, where we simply erased the central channel. And I was part of the decision-making team that decided that that was our solution. But the more we lived with it, the more we realized that this just wasn't right, that we were basically negating one of the most important elements that gave this particular piece of earth its power. And so in 2016, we decided we really needed to treat the central torrent, treat this channel like a monument. A dynamic one, but one that was every bit as important to our archaeological understanding as were any of the buildings and retaining walls. It turns out it is actually our largest monument in the sanctuary. international team of Andrew Farrenholt Ward and Basalt Boulders and others worked to basically record this channel. They worked, Yanis Poulourakis was another, using photogrammetry and dividing it into sections, recording those sections, and then translating them into plans and elevations, and then coding them according to the period of intervention. And we were very careful to record not only the ancient constructions, but collapses, and also the several attempts in the 1950s to channelize this stream. And so you see both modern and ancient interventions here recorded. It allowed us to really understand some of the dynamics that were at work and very dramatically displayed. And it allowed us to revise some of our hypotheses. For example, you see here a section just west of the Rotunda of Arsinoe, where if you look at the right-hand aerial view, you can see a major section of Roman wall still surviving, a major section of collapsed wall against it that's actually belongs to the eastern side of the channel. And then where the blue arrow touches either side, you have another very large section of collapsed Roman concrete. We wondered if this could be a vault over the ravine, but it turns out no, it's the collapsed wall from the western side that's come down and come hit against the eastern wall. So this mapping was really productive to understand both the dynamics of construction and but also destruction. And it allowed us to understand the relationship of the boulder wall to the concrete one. You see in a kind of bright yellow the remains of the basalt Greek boulder wall here on the lower left-hand image, against which this massive concrete bridge landing has been built. That was interesting to us, just because we wondered, okay, well, how much has the channel actually moved between the original Greek and the Roman repairs. The other thing we realized was that the ancient and modern channels were not exactly aligned. The work that you are looking at on the right was chiefly done in the 1950s after some very bad storms, where there was an attempt to channelize the stream yet again. You can see how undermined that 1950s wall is today. You'll notice that in the Ward and Bayet plan, there's a section that's not doesn't have a photogrammetric color code, because there was simply no ancient wall that we knew of in that area. But in looking closely at the trajectory of the 2 points that we did have, they hypothesized that this current modern channel was significantly to the east of the ancient one. And so in 2019, we actually excavated in the area. Unfortunately, it was right in the area of the tourist path, so we opened up a small trench, but we found a really interesting situation that of collapse and of original wall. We also discovered just kind of wedged up against one of the collapsed pieces of wall, this beautiful Ionic column base, which doesn't belong to any of the Ionic monuments that we currently have. So we have yet another important Ionic building somewhere in the sanctuary to look forward to finding. On the final photogrammetric model at closing of excavation, I think you can see here several different layers of this collapsed wall and channel. And basically what we discovered, you can see this perhaps more schematically, but clearly on the image on the right, The blue is where the modern channel runs. The green is where the ancient one was. And so one can make out this area here is the collapsed eastern wall. This is the channel over to the right-hand side of the image. And then you have the collapsed Roman western wall, and then the boulder foundational part of the original boulder wall, all preserved here. Our plan, if we are able to work again in the sanctuary in 2021, this summer, is to work to the south of this trench to follow the line of the channel back closer towards the area of the theater. We also did want to look again at the relationship of the Hellenistic to the Roman wall in this particular area, and that was another part of our excavation where we did, in fact, follow along the line of the boulder wall that you can see just behind this huge concrete section of Roman wall. So right there, just continued. All right, now what we didn't find that we were hoping to was some evidence of the way in which the channel was bridged. And it's possible that we didn't find it because it was made of ephemeral materials. One of the ways that ravines of similar width are bridged in Samothrace today are through laying logs and across on a boulder retaining wall, and they are very operative. Here you have a band of goats crossing one such wall. But another idea to consider is the way in which the Samothracians frequently used corbelled arches to span distances. For example, in the ancient city wall. I favor the more ephemeral solution, and my colleague Andrew Farrenholt-Ward favors the more the corbelled arch solution. So we're still in discussion. The other issue, and this involves the work of Ian Burr and Arya Basu, is where to put the bridges. If we don't, we know we have one near the Rotunda, we know we have one near the theater, but we still need to be able to get back and forth across the channel in more than just those few places. And so we actually, since we're not finding physical evidence, we wondered, well, but what about patterns of movement? What about human action? Those are where we definitely have bridges. But so we asked Arya to create an interactive situation using the model in Unity, and he can say more about this. But I'll quickly run his program. Where what we've done is we have the model of the sanctuary, and we have a camera set at eye level, and Arya is operating the camera, and I just simply asked him, I need you to get across to the western side, and then I want you to go and be able to see the Huron, and I want you eventually to get to the theater. And this is the course he took, and you can trace it in the pink line. So he's sort of looking around. Well, okay, he decided he was going to go across at this point, but now he needs to get to the Huron. So we need a bridge somewhere around in this area here. And then actually, once he's at the Huron, all right, I have other animations that show that he actually needs to get back to the other side to get around the hall of votive gifts to be able to get to the altar court. But this is one of the kinds of tactics we're using to understand how people could have moved around in the sanctuary. Now, I think I have time to share with you also how important it was not only to get to the western side of the channel, but also up to the Stoa Plateau. Samothrace has, as Bill's explained, a very large stoa, 100 meters long, and it's always been thought that you could access it through the theater, but excavations in the 70s, 80s, and 90s blocked every other route up to the Stoa, and that remains curious to us. And we've been excavating in one region just known as Space K. I think if you can see my cursor, I'm circling it. I won't present that today because it remains inconclusive whether there was a set of stairs there, whether they were there at the time that the Stoa was or earlier is still a question we're attempting to answer. But we do have better information on the theater based on our excavations of 2018 that I would like to share with you. Now, the theater was in much better shape in the early 20th century than it is today. It was first uncovered by Charles Champoiseau. He was looking for the head of the Victory, and he worked his way from the bottom to the top, exposing it so that, but without success, at least for his purposes of finding the head of the Victory. But a team of French-Czech scholars came to the sanctuary in 1923, and they further uncovered the theater. And as you can see from their photographs, it had a number of still well-preserved seats. It had the upper retaining wall for the retaining wall for the upper koilon. It defined the diazoma. It preserved 4 kerkites at least. And they made a really pretty good plan. But as you can also see, they did not geolocate it in relationship to the Nikkei Monument above or the altar court and central torrent below. When Carl Lehmann came to the site, basically at first in 1937, the theater was virtually gone. And he blamed the local inhabitants. He said, I see pieces of the theater in their houses, but it was made actually of a very friable material. And here again, the work of Bill's work with petrography is critical. It's made of a porphyritic rhyolite, which disintegrates very rapidly when exposed to the air. And it's quite possible that the exposure from the 1920s, even to the end of the 30s, was enough to cause a number of these seats to disintegrate. So Lehmann actually never really excavated in the area of the theater, but he was very interested in the altar court, which is the building that faces the theater. And he came up with a design for the theater that met his understanding of the altar court. And he did so in the absence of the French-Czech work, which had remained unpublished. When they did publish their work, it was not until 1956, and then by later scholars, and then again in 1983. And this is the plan that François Salviat published of the region. And you can see there the French-Czech understanding of the theater is very different from that of Lehmann. And we wanted to understand which one of these designs best matched the evidence. And we needed to, because it was urgent. We needed to understand the role of the central channel. We needed to understand the relationship with the Nikkei Monument, and it became clear that both of them could be best understood if we had a better grasp of the theater. Now, the excavation was highly successful, even though what we have on the ground is not very much. You can see that we only have one theater seat that survives in situ. They're sort of in the middle of the screen. But the foundational material, again, our wonderful basalts and our trachytes and are laid out in great arcs that formed the footing for the limestone and porphyritic seats. And we might notice, it's hard to tease out, but these seats were made of a really beautiful, deep purple red material, this porphyritic rhyolite, which has outcroppings just to the south, just to our left in this image, although there also are quarries for the material. We have some fossiliferous limestone seats, And then, of course, there's a different material that was used right here at where the intersection of the Koilon with the orchestra, a kind of biotite tuff, which is a smoother and more dense stone. And then the basalts, which form the foundations and support the seating area. So this richness of material, you must kind of reimagine having both deep purpley red seats and limestone white seats. And as the French Czech team say, well, it's really rather random. There's seats are in one color and then they're in another. They attributed that to just exhausting one quarry, then going to another. But I think that we see other examples in the sanctuary of combining materials and not necessarily in what looks like an organized way, but I think it actually is in quite an evocative one. And while I wouldn't go so far as to say it's completely intentional, I think it was completely acceptable and not just pragmatic. Now, in terms of the design of the theater, what we were able to do was confirm the essential accuracy of the French Czech plan. And we did so, you can see on the left of the screen, our trenches, then our trenches overlaid with the French Czech plan, and then a potential reconstruction based on these two sets of evidence. What we don't have is a notion of the exact extent of the Koilon. It could be just made up of 5 Calcareous, now that, as the second image suggests, and that would not be unlike the theater at Thasos. Or you could have a complete kind of more traditional Greek theater design, as you see on the far right, with 7 Calcareous forming a little bit larger than semicircular design. And then a compromise sort of halfway in between there in the middle, where the lower area has more seating than the upper. And that is actually the one we chose because it best suits the physical setting of the site, but it is hypothetical. And here we return the plan, this new plan, to the overall state plan of the sanctuary, and you can see how very different it is from the one proposed by Lehmann, and which we've been using for the past half century about. The most important thing to notice is that it is further to the west and higher uphill. The orchestra is a great deal greater diameter, more like between 12 and 13 or 12 to 13 meters rather than the 9 that Lehmann suggested. The other really important thing to note is that because it's set further to the west, it's entirely possible to approach the theater along the western side of the ravine. We still do imagine that it's bridged here, but the altar court is on a very different elevation now, as we know from this excavation, and we have to actually build staircases that come up on both sides to reach the level of the orchestra and also the facade of the altar court. This is the 3D model that Ian has made of this new understanding of the sanctuary, and Ian has the patience of a saint, because we also had to have him move the channel to the west to reflect our new understanding of the particular position of the retaining walls. Here you get a general sense from what was preserved and some of our reconstruction of this opportunistic use of different kinds of materials that, to my mind, connect it kind of more organically with the landscape. And just to see the overlay of our model on the actual state, we can play this animation. Now, um, this takes me to my next topic, and I will very soon turn over to Arya Basu. But one of the reasons why we are so intent on creating this very refined three-dimensional model was that we really wanted to understand in this complex topography what a visitor could see. We created the model, and then we set it at eye level, a camera at eye level, and moved through the sanctuary. And it's interesting. To me, it was very important to control the view of what someone could actually see. This view that you're looking at now is actually one I took standing on the ground. But when other scholars have asked for renders of our model, and they'll all say, well, what exactly do you want? They almost always want something that's in the air. And I'll say, well, wouldn't you rather have what somebody could see? And people have, they say, well, no, actually, one can reorient and reconfigure ideas in your mind to get an aerial view. It's an interesting, debatable concept. For us, staying on the ground was imperative. And I just would like to take maybe the next 3 minutes to show you the animation we've made to move through the sanctuary. We did this for the new opening of the Samothrace Museum, and it lasted about 3 minutes. So if I can bear with me here. Well, Thanks very much for listening to some of our overview of work that we're doing to integrate materials, architecture, movement, landscape. But we have one more initiative that I would also like to share with you, and that's the work of Arya Basu to kind of reintroduce the idea of communal experience, because in that animation, as you realize, it was really the camera was at eye level, but there were no participants. And so this is what Arya Basu has been working on. And I therefore would like to turn over the seminar to Arya.
Bonsoir, everyone. It's evening in Paris, or France in general. And my name is Arya Basu. I'm a computer scientist by trade, and I work with Ian Burr and Bana Westcote and the rest of the Samothrace team at the Emory Center for Digital Scholarship. And we call our lab the Digital Visualization Lab. I just wanted to quickly say a little bit about me. Like I spent a lot of time in developing virtual reality applications, mostly immersive, and spent a lot of time studying human motion. And I have a sort of an overlap between computer science and human-computer interaction. I'm just giving you a backdrop because this will help maybe make you understand why I'm studying human motion in virtual reality. Real quickly, our visualization lab does these three major things. So we create and configure 3D models using a variety of computer modeling software, such as 3D Studio Max and others. We also work with simulation software and real-time game engines like Unity. And we also work with geospatial data in most of our projects. We also leverage graphic design, image processing, and apply data visualization to our digital scholarship projects at the center. And lastly, and most importantly, we promote and advance student training and professional development initiatives through our lab, and also Ian Burr and I offer a course on 3D visualization and modeling, and so in the college. So this next slide is sort of a snapshot of what we're doing currently, from Samothrace to Slave Voyages to Open World Atlanta. These are all like snapshots of all of our projects. And it's one of my favorite slides, actually. You can also see the Nikkei Monument there in pink and black backdrop. This was a specialized software called ZBrush, where we, because of its high resolution and high polygonal detailing, we couldn't open it up in regular software. And then we optimize. So I'll stem from this to more into the Samothrace project, but let me kind of talk to you about the real implications of what we are dealing with. So back in 1987, it was shown that to really mimic photorealistic experiences, it would equate to 80 million polygons per picture. So that's one screenshot. To mimic reality, it would require 80 million polygons. Polygons are units for 3D rendering or 3D geometry. And back in those days, it would translate to a VR world with 800 million polygons per second with 10 frames per second update rate, which is very low in consideration to what we can achieve now with faster GPUs and other computing advancements. But this slide, I use it as a perspective piece, because keep in mind to mimic photorealistic experience, immersive experience, phenomenological experiences, as if you're in Samothrace, that would equate to a lot of like heavy duty lifting on CPUs and GPUs, and we cannot really achieve a very fluid experience if we were to not optimize them. So optimization is a huge behind the scene technology and technique that we have to use all the time. Okay, so from there, I just quickly wanted to talk about the data flow or the workflow of how we work. We have Bana have been gracious to supply us with plates and architectonic blueprints and information. From there, we take those information into CAD as our first intervention, and then from there we bring all the details and ornate them in something called 3D Studio Max. And then finally, we go from a 3D representation, from CAD to a 3D representation to a finalized scene view in Unity. So I'm just painting a picture where it's an ecosystem of softwares, and we work within different software ecosystems to kind of like translate and preserve the details of each and every building and then the overall scene. So this is like the grand view of the sanctuary inside from the Unity scene. It's not complete. We still have to work on a lot of detail, and there are some newer changes and modifications since last year that Ian has been making with Bana. So we'll incorporate that. But just, you know, it takes an enormous amount of time to really like get things in from 3D Studio Max to Unity, and then preserve and integrate everything. And then finally, we also have to do a rigorous validation so that, you know, we're not changing the versions between 3D Studio Max and Unity. So I think Bana has showed you one pathway that we previously talked about. I'm going to play the scene, but then also talk in the background. So basically, this was a very fascinating and interesting question that Bana brought to me, and you know, because of my field and my exposure to human elements and human motion in the virtual paradigm, I suggested that why don't we study the movement as a pattern. So the question was, what is the most obvious way to cross the ravine and cross it back at many different points in the sanctuary? And so this video, I'll play it again. This video was one where we don't have any crossing. You're assumed to be a very athletic person, and you jump over the ravine from point to point. Maybe that was the case, we don't know, but this was without the bridge configuration, where the egocentric perspective, basically you as a character is moving between points and you're jumping to cross the ravine. So next slide is minimal crossing. So you have a wooden bridge, but only minimally connecting the ravine and, well, the ravine and the sanctuary. So here you have two. On the top view, you can see I I used the bridge and crossed across the ravine to look at some buildings. And then the third video is the third configuration of multiple and more efficient crossings, where you have more than what is needed so that you can go across the ravine at multiple points. And you see, by creating these three different scenarios, we are studying patterns, and then we can statistically, arrive or conclude that, this probably was the most efficient way to cross. It's still a work in progress, and as you can see, the state of the scene is not ornate, to say the least. It's the bare bones. But see, that's the other advantage of Unity, where you don't have to have the most highest resolution possible, or highest resolution models to populate the scenery. I mean, it can work with bare bones wireframes, and the whole intent of this investigation is not the beautiful renderings, but rather a more functional question that we can start asking. So that's the utility of a real-time interactive framework or platform like Unity. Okay, so next. Okay, so now I'm leading into that pathway question. So after a few, I would say, few weeks or some months, Bon and I, we started discussing, well, we can start to populate the space, because it's one thing to experience the egocentric perspective in isolation, but it's a whole new experience if you have crowd walking around you or along with you, and it just makes things more realistic. So we started to kind of like look into the pathways. What are the different profiles of these agents, so to speak? Like, One would be, so we were enumerating through different possible scenarios, and then one got stuck to our mind where we're saying, let's investigate the scenario where we have a leader profile, which is an initiate. Which is a which has a leader who has already been initiated, I'm presuming, and who knows the sanctuary very well. And then there are a group of initiates who follow the leader into the pathway. So this was a hand-drawn sort of brainstorming session where we were dissecting and dividing the sections of the pathway from the entrance of the sanctuary to the theatrical circle. And Donna, feel free to add anything you think is important, or anything if I'm saying it wrong. Feel free to chime in. So basically, from there we wanted to, we clearly understood that we cannot hard code a behavior. In other words, we cannot simulate a situation where we are dictating the terms. Rather, we should let these agents, so to speak, who can make up their decisions following certain rules and navigate the terrain. So I got to thinking maybe agent-based modeling is the way to go. And by the books, agent-based modeling is a system that is modeled as a collection of autonomous decision-making entities called agents. So basically, these agents have sensors, and they can scan their area, so to speak, and then they can come up with decisions based on some rules that I have, designed them in keeping that in mind. So each agent individually assesses their situation and makes decision on the basis of a set of rules. In this case, the set of rules is that a particular group of initiates would just follow the leader agent, and they'll have active collision detection and avoidance system where they would not bump into each other. Even though I say that, they do, and it could be, every iteration could be very funny to watch. So full disclaimer there. But basically, these agents, as I was saying, that they have a cone of vision, as this inverted pyramid suggests, and that cone of vision is their threshold of what they can look and where they can look in real time, and just observe and record and then make a decision. And it all happens in real time, so 60 frames a second at the very minimum. And then the second part that we had to set up was it's only half the equation if you just set the rules and you tell these agents to just navigate on a piece of land virtually, albeit, but that's not enough. So the other thing you have to do in Unity or in any other real-time gaming engine platform, I presume, that you would have to tell you would have to turn the terrain, the mesh, with a navigation mesh. And navigation meshes are basically these rule-based spaces where you say what areas of the space is permissible for navigation and what areas are not. And then you also set up height information, elevation, as if as if to let these agents know that now this is the most obvious terrain you have to walk, and then you have to be aware of certain rules. So I'm going to have to, comply to the rules of navigation for these agents, but then also set the navigation mesh in Unity so they both play each other nicely. And so this is my workflow and the interface where I set the agent radius, agent height, and all these different parameters for them to navigate the mesh. And on the left-hand side, you're seeing a chunk of the Samothracian landscape, the sanctuary. The reason we went with a smaller chunk is that, well, first of all, it's easier on the memory, and then also we needed to dissect each section, so we focused on just the entrance until they reach the theatrical circle. Okay. So I'm going to show you a video, and then I'm going to show you a live demonstration. So this is just an old video where I have a profile. I have the leader agent in pink, and then the cyan or greenish agents are followers, and they're trying to follow the leader, and the leader is supposed to know where he or she is going, and apparently it is confused. And that happens. I mean, this is just one iteration because they're computing in real time, and sometimes their vision can get clouded and they are not so sure where to go. And by the way, I should also mention that the leader profile has a waypoint mechanism, so it knows where to go from point to point. Rather, and the followers don't have such a thing. They're just following the leader blindly while trying to avoid colliding and with each other. And in this iteration, you can see one of the followers got lost. Yep. All right. So I'm gonna break it here, and I'm gonna go to the live demonstration. So this is, by the way, just a quick primer. This is the editor view. As you can see, I've set the scene up specifically on an ocean plane that has real-time global illumination to give you the effect of ocean around you, and then a smaller chunk of the entire Samothracian sanctuary, where I'm setting up the waypoint system, which is these tiny spheres with the I guess a velociraptor or a dinosaur icon. So ignore that. And then these are the collection of agents, so with their individual cone of vision. So let's see if this works. So I'm gonna play, and you'll see some things happening in real time. Yeah. So okay, so there are 4. I'm gonna stop this real quick, and I'm gonna show you one thing again. So see, the dynamic nature of Unity is this. Let me do that. Yeah. So as you can see, I'm adding more initiates. Like let's say add 40. I'm gonna add some really serious number of initiates here. There. Yep. And then there. Okay. So 1 to 39, and then there's another one. So let's play this scene again. This is the beauty of Unity, where you can functionally add whatever you want to do and analyze. It might seem a little unrealistic, but let them spawn. So every time step, they're trying to follow the initiate. The initiate is trying to, meander around them. And let's see if there's a clogging effect happening at the door of the entrance. I mean, as you can see, I mean, these there is an utility of why the entrance was designed in a way, and so we would be able to statistically understand why the door was in such a place, or if there are any crowd control mechanism by design in the architectural plan of the sanctuary. But this is a very computationally exhaustive way to do that. As you can see, yeah, there's clearly a crowd control. See, there's a stream of single line agents. I mean, the followers who are forming at the door, and this kind of signifies why the door was there. Potentially, I'm just thinking out loud. the leader got lost again, and it does that. I mean, it's not as perfect as I would want, but that's the nature of evolutionary computing. I'm not trying to hardcode behavior. I'm rather trying to evolve the behavior and observe what they do based on rules. I'm going to stop it here. I think it's tracing back its path. Okay. All right. It takes pardon, but I mean this program is enormous, so it takes a longer time to load. Okay, so yeah, to kind of like wrap it up, this is what our framework is, where we're trying to, so basically going back to the idea that we have a workflow where we're going from plans to a 3D representation to a final outcome. And this is just a futuristic slide what we're up against. So what we want to do is we want to try and work our way from map data or other blueprints to a 3D model, fully 3D model environment. And from there, we'd like to work on a framework where we can deploy the same content to different visualization paradigms, like augmented reality or partially immersive deployment, like as in wearing a headset, or something like number 2 here, which is full immersion, where you're being physically tracked and you have a head-mounted display to explore the 3D content. So yeah, with that, a big thanks to the American School of Classical Studies at Athens, the National Endowment for the Humanities, and all of the rest, including our team members. Bana, feel free to chime in now. I mean, I think I'm almost done, and we can perhaps open up for questions.
Thanks so much, Aria and Bill, and Ian is here too, and we're happy to answer any questions or further discussion that the group has.